What if I told you the universe is stitched together by invisible threads so powerful they could warp space and time? These are cosmic strings, ancient filaments left over from the birth of everything, lurking in the darkness between galaxies. Scientists believe these cosmic threads might be the universe's hidden architects, twisting gravity, distorting reality, and possibly even holding the blueprint for time travel. Today, we're unraveling 26 mind-bending theories that could rewrite everything we know about existence, from their eerie connection to dark matter to their potential as portals across the cosmos. These ideas aren't just science fiction, they're frontiers of real physics. So buckle up, we're diving into the tangled mysteries of spacetime itself. Picture the universe in its first chaotic moments, a seething cauldron of raw energy where the very fabric of reality was still taking shape. As the cosmos cooled, spacetime itself may have cracked under the pressure, leaving behind fractures called cosmic strings. These aren't physical threads like a spider's silk, but unimaginably dense flaws in the structure of existence. Think of them as scars from the universe's violent birth. What makes them so extraordinary is their staggering energy density. A single cosmic string thinner than an atom could pack more mass than an entire mountain range, warping space around it with gravitational forces powerful enough to bend light. Some theories suggest these relics could stretch across billions of light years, weaving through galaxies like invisible puppet strings. And here's where it gets even more fascinating. Their gravitational pull might have played a crucial role in shaping the cosmos as we know it. Galaxies cluster in ways that can't be explained by visible matter alone, leading scientists to wonder, could cosmic strings be the unseen architects guiding the universe's grand design? Their influence could solve long-standing mysteries, like why some regions of space are crowded with galaxies while others remain eerily empty. If these theories hold, cosmic strings aren't just remnants of the past, they're active players in the cosmic drama, still shaping the universe today. What if the universe has hidden highways where time itself bends and twists? Among the most electrifying theories about cosmic strings is their potential to distort spacetime so dramatically that they could create time loops, paths where the future circles back to the past. Picture two cosmic strings whipping through the cosmos at nearly the speed of light. If they pass close enough to each other, their immense gravitational pull might twist spacetime into a knot, forming what physicists call a closed time-like curve. In this scenario, the fabric of reality becomes so warped that time no longer flows in a straight line, it folds back on itself. Suddenly, the idea of time travel isn't just science fiction, it's a mathematical possibility. Some researchers suggest these twisted regions of spacetime could act like natural wormholes, shortcuts that bridge distant moments in time. Imagine stepping through one end and emerging decades, even centuries in the past or future. But here's where things get even stranger. These cosmic time loops could introduce baffling paradoxes. What happens if you traveled back and altered an event that prevented your own journey? Would reality split into alternate timelines, or would the universe somehow correct the contradiction? While these questions remain unresolved, one thing is clear: if cosmic strings truly can twist time itself, they might hold the key to understanding some of the deepest mysteries of existence. Could these cosmic threads be the universe's way of weaving time into something far more fluid than we ever imagined? For decades, dark matter has been the universe's most stubborn mystery, an unseen force holding galaxies together while leaving no trace of its presence. But what if we've been overlooking something right in front of us, or rather, threaded through the cosmos? Some physicists suspect cosmic strings might not just be exotic spacetime oddities. They could be the very fabric of dark matter itself. Unlike ordinary matter, these strings wouldn't reflect or emit light, making them effectively invisible. yet their sheer mass concentrated into unfathomably thin filaments could explain why galaxies spin faster than visible matter alone should allow. Picture the Milky Way as a carousel. The stars we see aren't moving fast enough to keep it from flying apart, yet something unseen grips them in place. Cosmic strings could be that hidden hand, their gravitational pulls silently maintaining cosmic order. The implications are staggering. If strings make up even a fraction of dark matter, they'd rewrite the rules of particle physics. Unlike hypothetical dark matter particles, these relics wouldn't require new physics. They'd be a natural consequence of the universe's explosive birth. Researchers are already modeling scenarios where tangled networks of cosmic strings act as gravitational scaffolding, guiding galaxies into the vast webs we observe today. But the hunt is far from over. Detecting something so dense yet so slender pushes our technology to its limits. Some propose searching for telltale flickers in starlight as strings pass between us and distant stars, while others study gravitational waves for subtle tremors caused by their vibrations. If either method succeeds, it wouldn't just solve the dark matter puzzle, it would reveal a universe woven together by threads of pure spacetime. What if we could hear the universe's hidden vibrations, ripples in spacetime carrying echoes from the most exotic objects in existence? Cosmic strings might not just warp space, they could be cosmic tuning forks, sending out gravitational waves with every tremor or sudden snap. Unlike black hole collisions, which create brief bursts of gravitational waves, a vibrating cosmic string would produce a continuous hum, a steady drone in the cosmic background. Picture plucking a guitar string, but one that stretches across galaxies, vibrating at frequencies so low they'd take years to complete a single oscillation. Observatories like LIGO and future detectors could tune into these signals, hunting for patterns that betray the presence of these space-time threads. The most dramatic possibility, a cosmic string snapping under its own tension. If one of these ultra-dense filaments broke, the energy released would send shockwaves through spacetime itself, a gravitational tsunami detectable across the universe. Researchers speculate these bursts could carry unique fingerprints, revealing details about the string's size, age, and even how it interacts with other cosmic structures. But there's a twist. Unlike black holes or neutron stars, cosmic strings wouldn't just warp spacetime, they'd cut through it. Their razor-thin edges could create abrupt, knife-like distortions in gravitational wave signals, unlike anything we've observed before. Spotting these anomalies would be like finding a surgeon's scalpel in a pile of hammers, a clear sign that something far stranger is at work. For now, the hunt remains open. While no definitive cosmic string wave has been detected yet, each new gravitational wave observation brings us closer to either confirming their existence or forcing us to rethink the universe's most elusive structures. One thing's certain, if these whispers from the cosmic dark are real, they'll rewrite our understanding of gravity itself. There's a pattern etched across the cosmos, one so vast it defies comprehension. Galaxies don't drift randomly through space. They cluster along sprawling filaments, forming a luminous web stretching billions of light years. But what sculpted this structure? Enter cosmic strings, hypothetical threads that might not just exist within this web but could have actively woven it. Their role would be subtle yet profound. Picture a spider spinning silk between branches, each strand pulling objects into alignment. Cosmic strings could function similarly, their immense gravitational influence nudging matter into place during the universe's early expansion. As galaxies formed, they'd naturally clump around these invisible guide wires, like dew gathering on a spider's web. This could explain why galaxies often align in long, thread-like chains rather than dispersing uniformly. The evidence lies in the voids, the vast, empty regions between galaxy clusters. If cosmic strings seeded the cosmic web, their gravitational pull would have siphoned matter toward them, leaving behind these enormous bubbles of near-nothingness. Simulations show that string-like structures can recreate the universe's observed large-scale distribution far more accurately than models relying solely on dark matter. Yet the most intriguing implication is timing. Cosmic strings would have begun shaping the universe within moments of the Big Bang, long before galaxies even existed. This means the blueprint for today's cosmic web might have been etched into spacetime when the universe was hotter than a star's core. If confirmed, it would mean we're not just mapping the universe's current structure, we're glimpsing the frozen echoes of its birth pangs. The search is now focused on subtle clues, slight warps in galaxy orientations, unusual temperature fluctuations in the cosmic microwave background, or even unexpected ripples in gravitational waves. Each could be a breadcrumb leading us closer to understanding whether the universe's grand design was literally threaded into existence. At the quantum level, the early universe wasn't just a swirling chaos, it was a roiling sea of energy fields constantly flickering between states. In that turbulent infancy, tiny irregularities in these fields could have grown into something far more permanent, cosmic strings. Think of it like ice forming on a pond. As the universe cooled, regions of space might have frozen at slightly different energy levels, creating cracks in the fabric of reality, defects that became these unimaginably dense threads. This idea bridges two seemingly separate worlds, quantum mechanics and cosmology. The same unpredictable jitter that governs subatomic particles could have sculpted structures on a cosmic scale. It's a staggering thought that randomness at the smallest levels might have left scars stretching across the entire observable universe. But here's the real puzzle. If cosmic strings truly emerged from quantum fluctuations, they'd carry clues about physics far beyond our current theories. Some researchers suspect these strings could be relics of a grand unified force, a time before gravity, electromagnetism, and nuclear forces split apart. Their very existence might hint at hidden layers of reality, dimensions or particles we've yet to discover. Yet detecting these quantum echoes isn't easy. Unlike particle collisions in a lab, cosmic strings would preserve conditions from the universe's first trillionth of a second, a snapshot of physics at energies no accelerator could ever replicate. If we could study them, it would be like unearthing a fossil from the dawn of time itself, one that holds secrets about how all forces in nature once intertwined. The search is alive in unexpected places, from subtle twists in the cosmic microwave background to anomalies in particle interactions. Scientists are piecing together whether these quantum defects shape the cosmos, or if they're just another tantalizing dead end. Either way, the hunt forces us to confront a profound question. Did the universe's smallest quirks give rise to its largest structures? One of the most explosive possibilities about cosmic strings isn't just their existence, it's what happens when they die. Picture an ancient thread of spacetime, stretched taut over billions of years, finally unraveling under its own immense tension. The energy released in that instant could dwarf the brightest supernova, lighting up the cosmos with a flash so intense it might be visible across the universe. This isn't just speculation. Some theories suggest that the decay of cosmic strings could produce ultra-high-energy particles, cosmic rays with energies far beyond anything our most powerful particle accelerators can replicate. These particles would scream through space, potentially leaving behind signatures like gamma-ray bursts or mysterious bursts of radio waves, the wildest part. Astronomers may have already recorded these events without recognizing their true origin. Take gamma-ray bursts, for example. These fleeting but colossal explosions are some of the most energetic phenomena we've ever observed, often appearing randomly across the sky. While most are attributed to collapsing stars or colliding neutron stars, a handful defy explanation. their energy profiles don't quite match known astrophysical sources. Could these outliers actually be the final moments of cosmic strings snapping out of existence? The clues don't stop there. Certain fast radio bursts, brief, intense pulses of radio waves from deep space, have patterns that don't align with known celestial objects. One tantalizing idea is that these could be echoes of cosmic string vibrations, like the reverberations of a plucked guitar string echoing through the cosmos. If true, it would mean these elusive threads aren't just passively drifting through space, they're actively announcing their presence in bursts of raw energy. Detecting these signals would require a paradigm shift in how we interpret cosmic anomalies. Instead of searching for strings directly, scientists might uncover them by re-examining old data with new eyes, connecting dots between seemingly unrelated high-energy events. It's a reminder that sometimes the universe's most profound secrets aren't hidden in the shadows, they're flashing right in front of us, waiting to be deciphered. The implications are staggering. If decaying cosmic strings are behind even a fraction of these unexplained bursts, it would mean these space-time relics aren't just fossils of the early universe. They're dynamic, volatile, and capable of shaping the cosmos in ways we're only beginning to imagine. And that raises a thrilling question. How many more of these energy beacons are out there, silently counting down to their final, spectacular moments? What if our universe isn't alone, but instead just one thread in a vast cosmic tapestry? The eighth theory takes us into mind-bending territory, where cosmic strings might not just weave through our reality, they could stitch entire universes together. Imagine these space-time defects as nature's own wormholes, threading through the fabric of existence to link parallel worlds. This idea springs from a collision of two extraordinary concepts, string theory and the multiverse. In string theory, the fundamental building blocks of reality aren't particles, they're tiny, vibrating strings of energy. Now scale that idea up to cosmic proportions. What if these same principles gave rise to gargantuan strings during the Big Bang, one so massive they pierce through the boundaries between universes? It's a staggering thought. A cosmic string stretching between realities would act like a gravitational lifeline, a bridge where the laws of physics might subtly shift as you travel along it. Some models suggest these strings could even carry traces of other universes' unique properties, imprinting faint anomalies on our own cosmos. Picture finding a crack in a wall and realizing it leads not to another room but to an entirely different dimension. But how would we detect such a thing? The clues might lie in the unexplainable. Unexplained gravitational lensing, where light bends in ways that defy known mass distributions, could hint at a string's hidden connection to another universe. Or perhaps bizarre particle behaviors near these strings would betray the influence of alien physics seeping through. Of course, this remains speculative, but the implications are irresistible. If true, cosmic strings wouldn't just be relics of our universe's birth, they'd be portals to realities beyond our wildest imagination. And that raises an exhilarating possibility. Could these space-time threads be the ultimate proof that we're part of something far grander than a single cosmos? As wild as it sounds, the math doesn't rule it out. Some versions of string theory and brain cosmology actively predict such bridges, threading through higher dimensions we can't yet perceive. Whether they're real or not, the idea alone stretches our understanding of existence, forcing us to ask, are we standing at the edge of an infinite multiverse, connected by strings we've only just begun to fathom? Here's the next part of your script, crafted to flow seamlessly from where we left off while introducing fresh insights about cosmic strings and black holes. There's a dark corner of cosmic history where two of the universe's most enigmatic phenomena might collide: cosmic strings and black holes. Forget the colossal black holes formed by dying stars. These would be something far stranger. If certain theories hold, cosmic strings could have birthed black holes in the universe's earliest moments, leaving behind primordial relics that still haunt the cosmos today. Picture a cosmic string stretched to its limit, vibrating violently until snap, it fractures. The energy at that breaking point wouldn't just dissipate. Under the right conditions, it could collapse inward, warping spacetime so intensely that a black hole forms in its wake. Unlike stellar black holes, these wouldn't come from the death of a star, but from the death of a spacetime defect itself. The result, ancient black holes, possibly lighter than a speck of dust or heavier than a planet, scattered invisibly across galaxies. This idea isn't just theoretical sleight of hand. Primordial black holes could solve multiple cosmic puzzles at once. For instance, some of the universe's unexplained gravitational signals, tiny ripples with no obvious source, might trace back to these hidden remnants of snapped strings. Even more intriguing, they could be prime suspects in the hunt for dark matter. If enough of these black holes formed in the early universe, their collective gravity might explain why galaxies rotate faster than visible matter alone should allow. Yet detecting them is a colossal challenge. Unlike star-born black holes, these wouldn't be surrounded by glowing accretion disks or paired with companion stars. They'd be lone wolves drifting silently through space, but scientists aren't without strategies. Some hunt for telltale flashes when a primordial black hole passes in front of a star, bending its light like a lens. Others listen for the faint echoes of their collisions, which would produce gravitational waves distinct from those of larger black holes. The implications are profound. If cosmic strings truly forged black holes, it would mean some of the darkest objects in existence are also the oldest time capsules from the universe's first terrifying seconds. And that raises a chilling question. Could the voids we see in space today be dotted with black holes that aren't just dead stars but the corpses of cosmic strings themselves? The universe has its own hidden rulebook, one written not in words, but in fields of energy that dictate how matter behaves. Among these, the Higgs field is arguably the most famous, the invisible force that endows particles with mass. But what if cosmic strings, those spacetime scars from the Big Bang, left their mark on this foundational field? Here's the fascinating intersection. In the universe's earliest moments, the Higgs field hadn't yet settled into its current state. It was fluctuating wildly, like a stormy sea searching for calm. As cosmic strings threaded through this chaos, their immense energy could have warped the Higgs field around them, creating temporary pockets where the rules of mass worked differently. These distortions wouldn't just be ancient history. They might have imprinted lasting effects on how particles behave today. For particle physicists, this is like discovering marginal notes in nature's grand manuscript. If cosmic strings altered the Higgs field's behavior even briefly, those tweaks could linger in subtle ways, perhaps showing up as tiny anomalies in particle collisions at labs like CERN. Imagine detecting a particle interaction that defies expectations, only to realize it's carrying echoes of a cosmic string's gravitational fingerprint from the dawn of time. These deviations, once dismissed as noise, might be the universe whispering its deepest secrets, but the implications stretch beyond particle physics. Cosmologists propose that these Higgs string interactions could explain why the universe's expansion accelerates in certain regions while matter clumps in others. It's as if cosmic strings didn't just weave through space, they left behind a gravitational breadcrumb trail, guiding how structures formed while subtly tweaking the laws governing mass itself. The hunt for these imprints is already underway. Researchers are refining models to predict how such interactions might appear in particle accelerators or gravitational wave data. Others are reanalyzing the cosmic microwave background for asymmetries that could betray a Higgs field forever altered by primordial strings. If found, it would bridge two of physics' greatest puzzles, revealing how the universe's largest structures and smallest particles are inextricably linked by threads of spacetime. This isn't just about solving old mysteries, it's about uncovering layers of reality we never knew existed. If cosmic strings touched the Higgs field, they didn't just shape the cosmos, they might have rewritten the very rules of existence in their wake. And that leaves us with an electrifying question. What other invisible handshakes between cosmic forces are waiting to be discovered? Deep in the voids between galaxies, cosmic rays streak across the universe at energies that baffle scientists, some packing millions of times more punch than anything our most powerful particle colliders can produce. For decades, their origins remained one of astrophysics' greatest unsolved puzzles. But what if the answer lies in the gravitational whirlpools surrounding cosmic strings? These spacetime filaments could act as nature's ultimate particle accelerators. Picture a cosmic string's immense gravitational field as a cosmic slingshot. Charged particles like protons caught in its pull would whirl around it at nearly the speed of light, gaining unimaginable energy before being flung into the void. Unlike Earth-bound colliders, which require kilometers of machinery, strings would achieve this effortlessly, powered solely by the raw warp and weft of spacetime itself. The numbers are staggering. Some models suggest these interactions could propel particles to energies exceeding 10 to the 20th electron volt, enough to make a single subatomic particle hit with the force of a baseball pitched at 60 miles per hour. Astronomers have detected cosmic rays at these extreme energies, yet their sources remain elusive. No known astrophysical objects, not colliding galaxies, not pulsars, not even supermassive black holes, seem capable of producing them routinely. But cosmic strings, their unique physics makes them ideal candidates. Here's why this matters. If strings are indeed cosmic ray factories, they'd leave distinctive fingerprints. Particles accelerated by strings wouldn't just be energetic. They'd arrive in patterns that mirror the string's theoretical distribution across the sky. Recent observations from observatories like the Pierre-Auger Array have hinted at unexplained clustering in ultra-high-energy cosmic ray directions, sparking renewed interest in this possibility. Yet the plot thickens further. These particles wouldn't just tell us about strings, they might carry encoded details about the early universe's structure. As they travel through space, ultra-high-energy cosmic rays interact with background radiation, creating secondary particles. By studying these cascades, scientists could reverse engineer the rays' journeys, potentially tracing them back to string interactions billions of years ago. While the evidence isn't yet conclusive, the implications are electrifying. If confirmed, cosmic strings wouldn't just be relics, they'd be active cosmic engines, still shaping the universe by firing particle bullets across intergalactic space. And that transforms them from theoretical curiosities into key players in one of astronomy's longest-standing mysteries. In the afterglow of the Big Bang, a cryptic pattern lingers, one so perplexing that cosmologists dubbed it the axis of evil. This isn't science fiction, it's a real, unexplained alignment etched into the cosmic microwave background, the universe's oldest light. What makes it so unsettling? The temperature fluctuations in this primordial radiation should be randomly scattered, yet they form eerie, coherent arcs that seem to point in the same direction, almost as if the early universe had a preferred axis. Now here's where cosmic strings enter the mystery. These spacetime defects with their immense gravitational pull could have acted like invisible fingers, dragging matter and energy into unnatural alignments as the universe expanded. Picture a sheet of fabric warped by a taut thread beneath it. Cosmic strings might have similarly twisted the fabric of spacetime on a universal scale, imprinting their influence on the cosmos's very first structures. The implications are staggering. If strings caused the axis of evil, it would mean the universe isn't as isotropic or uniform in all directions as we once believed. Instead, hidden threads left over from its birth might have given reality a subtle but detectable tilt. This would challenge a cornerstone of modern cosmology, the cosmological principle, which assumes the universe looks roughly the same no matter where you observe it from. Yet the evidence remains tantalizingly indirect. Some simulations show that strings could create such anomalies by creating vast gravitational waves during their formation, ripples that would nudge matter into alignment. Others suggest that strings' unique ability to warp spacetime around them might have left behind a kind of cosmic wake, pulling the early universe's plasma into coherent patterns before it even cooled into atoms. But skepticism persists. Could this just be a statistical fluke, a trick of how we map the sky? Or is it the fingerprint of something far stranger, a relic from when the universe's fundamental forces were still intertwined? The debate rages on, but one thing is certain. If cosmic strings explain the axis of evil, they're not just remnants of the past. They're celestial signposts pointing us toward a deeper, more textured understanding of reality itself. For now, the hunt continues. New telescopes probing the cosmic microwave background, like the Next Generation CMB-S4 project, could finally reveal whether these alignments are mere coincidence or the ghostly handiwork of cosmic strings. Either way, the answer will force us to rewrite the story of how the universe chose its shape and what or who might have been pulling the strings all along. Imagine the universe as a house of cards perfectly balanced, but with one precarious thread capable of bringing it all crashing down. That's the spine-chilling premise behind vacuum decay, a theoretical doomsday scenario where cosmic strings could flip the fundamental rules of reality in an instant. Here's how it works. The vacuum of space isn't truly empty. It's a seething quantum field locked in what physicists call a false vacuum, a stable but not perfectly stable state, like a ball resting in a shallow valley. Cosmic strings, with their unimaginable energy density, could act like a nudge to that ball, sending it tumbling into a deeper valley, a true vacuum, the difference. In this new state, the laws of physics as we know them could rewrite themselves. Atoms might unravel, forces could reconfigure, and the universe as we recognize it would cease to exist. The good news, this isn't a likely event. Most models suggest our vacuum is extremely durable, like a valley so deep the ball would need a cosmic bulldozer to dislodge it. But the mere possibility underscores how profoundly cosmic strings could warp existence. They're not just relics, they're potential triggers, carrying enough concentrated energy to destabilize the quantum fields that underpin everything. What's truly fascinating is how this ties into the broader puzzle of cosmic strings' lifespan. Some theories suggest older strings could grow unstable over billions of years, vibrating violently until they snap, not just breaking themselves, but potentially cracking the vacuum around them. If even one string triggered such an event, the resulting bubble of true vacuum would expand at light speed, erasing the old universe in its wake. Yet there's a twist. This apocalyptic scenario might also be a creative force. In a multiverse model, vacuum decay could birth entirely new universes with different physical laws, each one a cosmic phoenix rising from the ashes of the old. It's a staggering thought. The same strings that might end our universe could plant the seeds for others. For now, vacuum decay remains in the realm of mathematical possibility, but it forces us to confront the universe's fragility. Cosmic strings aren't just cosmic curiosities. They're reminders that reality, for all its apparent solidity, might be balanced on a knife's edge. And that raises a humbling question. Could the threads stitching spacetime together also be the ones that someday unravel it all? Somewhere in the depths of intergalactic space, an invisible titan exerts its pull, a gravitational behemoth so powerful it's dragging entire galaxies toward it. Astronomers call it the Great Attractor, a mysterious region roughly 250 million light-years away that warps the motion of everything around it, including our own Milky Way. But what cosmic force could wield such influence? The answer might lie in the silent, unseen tension of cosmic strings. Unlike black holes or galaxy clusters, which announce their presence with light or radiation, cosmic strings could be distorting spacetime without any visible trace. Imagine draping a bowling ball on a trampoline. The fabric dips dramatically where the mass sits. Now picture that same effect caused by something infinitely thinner than an atom yet dense enough to bend the universe itself. If a cosmic string threads through the Great Attractor's vicinity, its gravitational pull could easily explain why galaxies are veering off course as if caught in an invisible current. The numbers align eerily well. A single cosmic string spanning hundreds of millions of light-years could generate enough gravitational distortion to mimic the Great Attractor's effects. No exotic dark matter or hidden supercluster required. Even stranger, these strings wouldn't just tug matter toward them. They'd warp the very grid of space-time around them, creating a directional flow that galaxies simply can't resist. It's as if the universe built hidden rivers of gravity, and everything within their reach is drifting downstream. Yet the mystery deepens. The Great Attractor isn't just pulling. It's shrouded in a zone of space obscured by our own galaxy's dust, making it nearly impossible to observe directly. This cosmic blind spot means we're left inferring its properties indirectly, precisely the kind of scenario where cosmic strings could operate undetected. Some researchers speculate that multiple strings could even intersect there, amplifying their gravitational footprint into something colossal enough to steer galaxies. The implications stretch beyond a single anomaly. If strings are behind the Great Attractor, they might be responsible for other unexplained gravitational flows across the cosmos. Surveys of galaxy motions have revealed additional large-scale, dark flows, regions where entire superclusters march in unison toward some unseen force. Each could be another hidden string, silently orchestrating the universe's grand motion. For now, the puzzle remains unsolved, but future telescopes like the Euclid Space Observatory could map these gravitational distortions with unprecedented precision. If they detect patterns that align with cosmic string models, it would revolutionize our understanding of what shapes the universe's largest structures. Until then, the Great Attractor stands as a gravitational enigma, one that might not be a place at all, but the ghostly pull of a space-time thread woven through the cosmic dark. The universe might not be what it appears, not a three-dimensional expanse, but a vast cosmic illusion, like a hologram projected from the hidden edges of reality. This is the holographic principle, a radical idea suggesting everything we see, stars, galaxies, even our own bodies, could be shadows cast by information encoded on a distant, two-dimensional surface. And cosmic strings, those bizarre one-dimensional threads woven through space, might be the glitches in the projection. Think of it like a movie screen. The images appear lifelike with depth and motion, but they're ultimately just flat pixels rearranging. Cosmic strings could be the cosmic equivalent of a torn film strip, an artifact revealing the projection process itself. Their bizarre one-dimensional nature fits eerily well with holographic models, where true reality exists in fewer dimensions than we perceive. If true, these strings wouldn't just be relics of the Big Bang, they'd be literal seams in the fabric of the illusion. The math behind this is as elegant as it is mind-bending. In holographic theories, the information needed to describe a volume of space, say a galaxy, can be entirely encoded on its boundary, like data etched onto the surface of a sphere. Cosmic strings, with their infinite thinness and immense energy, might emerge as anomalies where this encoding strains or fractures. Picture a glitch in a video game where textures fail to load properly, revealing the underlying code. Strings could be spacetime's version of that glitch, exposing the universe's hidden scaffolding. But why would this matter? If cosmic strings are holographic artifacts, studying them could unlock clues about the fundamental nature of reality. Their vibrations or interactions might carry imprints of the lower dimensional source code projecting our universe. Some physicists speculate that collisions between strings could even momentarily disrupt the holographic field, creating localized distortions where the usual laws of physics briefly flicker, like a screen momentarily freezing before resuming playback. The search for evidence is already shifting paradigms. Experiments aiming to detect cosmic strings, gravitational waves, or light-bending effects aren't just hunting for exotic objects, they're probing whether the universe is a cosmic mirage. Future observatories might even spot patterns in string behavior that mirror holographic predictions, like echoes of a deeper mathematical structure governing all of existence. Whether the holographic principle holds or not, the mere possibility reshapes how we view cosmic strings. They're no longer just space-time oddities. They're potential Rosetta Stones, carrying translations between the universe we experience and the hidden dimensions that might truly define it. And that leaves us with a haunting thought. If strings are stitches in the hologram, what or who is holding the projector? One of the most unsettling predictions in cosmology isn't just the universe's expansion, it's how that expansion might one day shred everything to subatomic confetti. Known as the Big Rip, this apocalyptic scenario suggests that dark energy could grow so dominant that galaxies, stars, even atoms themselves will be torn apart in the universe's final moments. But hidden in this cataclysm might be an unexpected accomplice: cosmic strings. These space-time threads could act like hidden accelerants in the cosmic fire. While dark energy drives the universe's accelerating expansion, cosmic strings add another layer of tension literally. Picture space as a rubber sheet being stretched from all sides. Normally, it would thin out gradually, but cosmic strings are like tiny, ultra-dense knots in that sheet. As expansion pulls them taut, their incredible energy density could create localized stress points, amplifying the surrounding strain. Over billions of years, these microscopic flaws might become cosmic fault lines, places where space-time starts to fray long before the final rip. The math behind this is as chilling as it is elegant. Most Big Rip models assume a uniform dark energy force, but cosmic strings introduce wild cards, tiny regions where gravity warps unpredictably. Some simulations suggest that strings could concentrate dark energy's effects, like focusing sunlight through a magnifying glass. In certain scenarios, their gravitational pull might even hasten the universe's demise by destabilizing the fabric of reality in their immediate vicinity, triggering premature ruptures in otherwise stable regions. Yet here's the twist: cosmic strings might also leave behind a cryptic warning system. As they vibrate under increasing tension, they could emit gravitational waves with a distinct rising frequency signature, a cosmic death hum detectable by future observatories. These waves wouldn't just reveal the string's locations, they might serve as an early alarm for the universe's unraveling, giving advanced civilizations, if any survive, a countdown to the end. Of course, this remains speculative. The Big Rip itself hinges on dark energy's still mysterious properties, and cosmic strings' role is even less certain. But the possibility forces us to confront a profound irony. The same threads that might have woven the universe together in its infancy could, in its final act, help pull it apart. Whether they're key players or minor actors in this cosmic tragedy, one thing's clear: if strings exist, they're not just relics of the past, they're silent witnesses to whatever fate awaits us all. The search for answers isn't just about doom-scrolling the universe's future. By studying how cosmic strings interact with dark energy, cosmologists could unlock clues about the fundamental forces governing expansion itself. After all, if spacetime has an expiration date, we might as well read the fine print. In the vast tapestry of cosmic theories, few are as daring as the ekpyrotic universe, a model where our entire reality arises not from a single Big Bang, but from an endless cycle of collisions between higher dimensional worlds. And woven into this grand saga could be cosmic strings, not just remnants of our universe's birth, but ancient scars from collisions that birthed countless universes before ours. The ekpyrotic scenario unfolds like an infinite cosmic tango. Picture two immense membrane-like structures called brains floating in a higher dimensional space. When they collide, the energy released sparks a new universe into existence, expanding and cooling until the cycle repeats. It's a vision where time has no true beginning or end, only eternal rebirth. But here's the twist. These titanic brain collisions might have left behind more than just heat and particles. They could have spun off cosmic strings like cosmic lint from a dimensional dryer. These strings wouldn't be ordinary spacetime defects. In ekpyrotic models, they'd carry imprints of the higher dimensional clash that created them, perhaps vibrating in ways that betray the existence of dimensions beyond our own. Some theories even suggest that strings could act as bridges between cycles, threads that persist from one universe to the next, carrying echoes of past realities into the newborn cosmos. Imagine finding a fossil older than the universe itself, whispering secrets from a time before time. The implications are staggering. If cosmic strings in our universe are relics of a pre-Big Bang event, studying them could offer a backstage pass to the ultimate cosmic drama, the moment our reality was born from the wreckage of colliding dimensions. Their gravitational waves, for instance, might encode the energy scale of the original brain collision, while their distribution could reveal whether our universe emerged from a clean hit or a chaotic, glancing blow. Yet the most tantalizing possibility is cyclical survival. If strings endure across multiple universe generations, they might serve as cosmic archaeologists' ultimate tool, a way to probe not just our universe's origins, but the infinite chain of creations that came before. It's a humbling thought. The same threads that might weave galaxies together today could be the untangled remains of universes long forgotten, waiting for us to decode their story. For now, the ekpyrotic model remains speculative, and the hunt for proof continues. But whether it's confirmed or not, the mere idea reshapes how we view cosmic strings not as passive remnants, but as potential messengers from a reality far stranger than we ever imagined. And that leaves us with a haunting question. If our universe is just one page in an endless cosmic chronicle, how many other threads from past worlds are still out there, humming silently in the dark? Here's your next segment, crafted to flow naturally from the previous theories while introducing fresh perspective on cosmic strings and the Fermi paradox. Among the cosmos' greatest mysteries isn't just what's out there, but why it's so quiet. Despite billions of potentially habitable planets, we've found no traces of advanced civilizations. This eerie silence, known as the Fermi paradox, has spawned countless explanations. Maybe aliens avoid us, or perhaps intelligent life is extraordinarily rare. But there's another, darker possibility, one where cosmic strings act as cosmic landmines, rendering vast regions of space lethally uninhabitable. These spacetime threads could be more than just gravitational oddities. They might be natural particle accelerators gone rogue. Picture a cosmic string vibrating violently, flinging off bursts of gamma rays or ultra-high-energy cosmic rays like shrapnel from an exploding wire. Any planetary system within range would be bombarded with radiation intense enough to strip atmospheres, mutate DNA, or even sterilize entire galaxies over cosmic timescales. The chilling implication: civilizations could arise only to be wiped out by invisible threads they never saw coming. The timing adds another grim layer. Cosmic strings aren't static, they decay, snap, or collide over billions of years, releasing catastrophic energy in unpredictable bursts. A habitable planet might thrive for eons, only to have its luck run out when a nearby string fractures without warning. It's like living on a fault line where the earthquakes arrive once every 100 million years, long enough to forget the danger, but inevitable all the same. Yet this theory isn't without hope. If strings are indeed galactic killers, their distribution could reveal safe zones, regions where civilizations might endure long enough to reach the stars. Astronomers could map high-risk areas by tracking gamma-ray anomalies or gravitational wave patterns, offering a survival guide for any species wise enough to decode it. Of course, cosmic strings aren't the only solution to Fermi's paradox, but they're among the few that leave tangible evidence. Future telescopes might spot the aftermath of these sterilizing events, planets with charred atmospheres or stars surrounded by debris belts where biology once had a chance. Until then, the string's role remains a haunting question, one that turns the search for extraterrestrial life into a forensic investigation of cosmic crime scenes. Whether they're the universe's silent assassins or mere bystanders, cosmic strings force us to confront a humbling idea. The greatest threat to life might not be supernova or black holes, but defects woven into spacetime itself, flaws that turn the cosmos into a maze with invisible, deadly walls. And that raises a sobering thought. If we are alone, it might not be by chance, but by design of a universe stitched together with threads too dangerous to touch. Imagine two particles separated by billions of light years, mysteriously mirroring each other's movements as if connected by invisible threads. This bizarre phenomenon is quantum entanglement, where objects share a bond that defies space and time. Now take that spooky action and stretch it across cosmic scales. What if the universe's most colossal structures, cosmic strings, carried this same eerie connection, tying distant corners of reality together in an instant? This isn't just wild speculation. Quantum entanglement typically plays out in labs with tiny particles, but the same principles could apply to these space-time defects. Picture a cosmic string vibrating in one galaxy. Its entangled counterpart, halfway across the observable universe, might shudder in perfect sync, bypassing the speed of light as if the distance between them didn't exist. Einstein famously called entanglement spooky, but at this scale it would rewrite the rules of cosmic communication. Why does this matter? If entangled cosmic strings exist, they'd challenge everything we know about locality, the idea that objects can't influence each other faster than light can travel. Instead, the universe might be stitched together by a hidden quantum fabric, where changes in one thread ripple instantly to its partners, no matter how far apart they are. Some physicists theorize this could explain strange, large-scale alignments in galaxy clusters, or even anomalies in the cosmic microwave background, patterns too precise to be mere coincidence. But here's the twist. These strings wouldn't just passively link distant points, they could actively funnel information or energy across the cosmos. Black holes might use them to teleport matter through wormholes, or advanced civilizations could exploit them for near-instantaneous communication. The catch: detecting such entanglement would require spotting correlations in cosmic events separated by unimaginable distances, a task so daunting it might demand an entirely new kind of astronomy. For now, the idea remains a tantalizing what if. Yet the mere possibility forces us to confront a universe far stranger than we imagined, one where the threads weaving spacetime together might also be whispering secrets across the void, binding existence into a single entangled whole. And if that's true, the cosmos isn't just vast, it's intimately, inexplicably connected in ways we've only begun to glimpse. For decades, the Pioneer 10 and 11 spacecraft carried a puzzling secret. As they ventured beyond our solar system, scientists noticed something bizarre. The probes were slowing down ever so slightly more than physics predicted. This tiny deviation, dubbed the Pioneer Anomaly, became one of space exploration's most persistent mysteries. While most explanations pointed to technical glitches or the subtle push of thermal radiation, a radical theory emerged. What if unseen cosmic strings were gently tugging on the probes like invisible puppet masters? Here's how it could work. A cosmic string drifting near our solar system, even 1 light-years away, would warp spacetime around it, creating a gravitational gradient subtle enough to escape detection but strong enough to influence objects over vast distances. As the pioneers traveled outward, their paths might have grazed this distorted region, experiencing an extra drag that standard models couldn't account for. Unlike dark energy, which uniformly accelerates the universe's expansion, a cosmic string's pull would be directional, acting like a silent current in the cosmic ocean. The timing adds another layer of intrigue. The anomaly's effects diminished as the probes moved farther from the sun, a pattern some argue aligns with a string's localized gravitational field rather than an onboard issue. If true, it would mean the pioneers didn't just explore the outer planets. They might have inadvertently brushed against one of the universe's most elusive structures. Skeptics, of course, point to simpler explanations. The anomaly's precise measurements eventually traced much of the deceleration to heat radiating unevenly from the probe's power systems. But even a final analysis left a tiny residual effect unaccounted for, a gap just wide enough to keep alternative theories like cosmic strings in play. What makes this idea tantalizing isn't just its audacity, but its testability. Future deep space missions could monitor for similar deviations, especially in regions where cosmic strings are theorized to cluster. A confirmed pattern might reveal not just the pioneer's unseen hitchhiker, but an entire network of hidden spacetime threads crisscrossing our galactic neighborhood. Whether the anomaly was a quirk of engineering or a brush with cosmic architecture, it reminds us that sometimes the universe's quietest clues, like a spacecraft slowing down a fraction too much, can point to its loudest mysteries. And if cosmic strings were the culprit, it would mean our first interstellar messengers encountered something far stranger than empty space on their journey into the unknown. Across the sky, faint whispers of the universe's birth still linger, an afterglow of radiation called the cosmic microwave background, or CMB. But nestled within this primordial light is something that shouldn't be there, a vast, puzzling chill known as the CMB cold spot. Stretching nearly 1 billion light-years wide, this region is colder than its surroundings by a fraction of a degree, a tiny difference but one that defies conventional explanations. Now, researchers are asking, could this cosmic anomaly be the shadow of a cosmic string? Gravity bends light, a fact proven every time we observe distant galaxies warped by massive objects in between. A cosmic string, with its unimaginable density, would do the same but with a far stranger twist. Unlike a black hole or galaxy cluster, which distorts light symmetrically, a string's ultra-thin yet ultra-massive structure would slice through spacetime like a razor, creating a unique lensing effect. If one drifted between us and the CMB, its gravitational pull could stretch and thin the ancient light passing through it, leaving behind a telltale cold patch in its wake. The cold spot isn't just a minor irregularity. Statistical analyses show its temperature dip is too extreme to be mere cosmic noise. Some theories suggest it's a supervoid, an enormous, empty region of space where the lack of matter subtly cools the CMB. But here's the catch: surveys can't find a void large or deep enough to explain the anomaly. That's where cosmic strings step in. Their gravitational weirdness doesn't require empty space, just spacetime itself bent in a way that mimics a void's cooling effect, like a funhouse mirror tricking the eye. Detecting a string's signature wouldn't just solve the cold spot riddle. It would crack open a new window into the universe's infancy. The CMB froze into existence just 380,000 years after the Big Bang, meaning any string imprint there would be a snapshot of these defects in their earliest state. The patterns within the cold spot, its shape, sharp edges, or secondary distortions, could reveal whether a string caused it, and if so, how these relics behaved when the cosmos was still in its cradle. Yet skepticism remains. The cold spot could still be a statistical fluke or something entirely unforeseen. Future observatories like the Simons Observatory or CMB S4 aim to settle the debate by mapping the CMB with unprecedented precision. If they find more cold regions with the same peculiar fingerprints, it could hint at an entire population of cosmic strings lurking in the cosmic dark, each one a frozen echo of the universe's first moments. Whether the cold spot is a strings calling card or just a cosmic curiosity, its mystery underscores something profound. Even the faintest glimmers of ancient light can carry clues to the universe's most enigmatic structures. And if we're right, this ghostly chill might not just be a patch of cold. It could be the first tangible trace of a space-time thread woven through reality itself. Time seems to move in only one direction. Eggs crack but never uncrack. Heat dissipates but never spontaneously concentrates. This stubborn one-way flow, known as the arrow of time, remains one of physics' deepest puzzles. But what if the answer isn't just in the laws of thermodynamics, but in the tangled threads of spacetime itself? Cosmic strings, those relics of the universe's birth, might hold the key to why time refuses to run backward. Here's the fascinating twist. At the quantum level, most physical laws work perfectly fine in reverse. A collision between particles looks just as valid whether you play it forward or backward, until entropy steps in. Cosmic strings could be the missing piece, introducing asymmetry on a cosmic scale. Picture a string slicing through spacetime like a flaw in a diamond, its immense gravitational field warping the paths of particles around it. Each interaction could leave a tiny, irreversible mark like a rock dropped into a pond, sending ripples outward but never inward. Over billions of years, countless such interactions might add up, nudging the universe toward entropy's inevitable climb. Some theories go even further. Strings vibrating or decaying could generate localized pockets where time's flow temporarily distorts, creating brief regions where causality stutters. Imagine a tangle of cosmic strings acting like cosmic hourglasses, their gravitational whirlpools selectively speeding up or slowing down time's passage. While we haven't observed such anomalies yet, they'd offer a tantalizing link between time's arrow and the universe's hidden architecture. Yet the most profound implication isn't just about explaining time's flow, it's about testing it. If cosmic strings truly break time's symmetry, their gravitational waves might carry a telltale signature, a subtle preference for one direction over another. Future detectors could hunt for these asymmetrical ripples, searching for echoes of a universe where time itself was woven into shape by defects in spacetime. Whether they're time's silent architects or mere bystanders, cosmic strings force us to reconsider a fundamental truth. The arrow of time might not be written in the stars, but in the scars left by the universe's violent beginnings. And that means the past, present, and future could all hinge on threads we're only just beginning to see. Imagine a cosmic library where every book ever written gets tossed into a shredder. That's essentially the black hole information paradox. According to quantum mechanics, information about particles swallowed by a black hole can never be destroyed. Yet black holes appear to erase it completely when they evaporate. This contradiction has baffled physicists for decades, but hidden in the tangled physics of cosmic strings might lie an elegant way to reconcile these two seemingly irreconcilable truths. Here's where spacetime's most enigmatic threads enter the puzzle. Unlike black holes which crush matter into oblivion, cosmic strings could act as cosmic backup drives, preserving quantum information in their gravitational whirlpools. Picture a black hole stretching spacetime around it like a funnel. If a cosmic string threads through that funnel, its unique geometry might imprint the doomed particle's information onto the string's structure like grooves on a vinyl record. Even as the black hole evaporates, that data wouldn't be lost, just encoded in the string's vibrations, waiting to be decoded. The math behind this is as fascinating as it is profound. Some quantum gravity models suggest cosmic strings could create soft hair, subtle gravitational imprints around black holes that store information in ways we're only beginning to understand. These wouldn't be physical strands, but rather patterns in spacetime's fabric, like invisible barcodes etched by falling matter. If correct, it means the universe has built-in redundancy, ensuring no data is ever truly erased, just relocated to a cosmic hard drive we've yet to fully access. But the implications stretch far beyond theory. If cosmic strings preserve black hole information, their gravitational waves could carry faint echoes of everything the black hole ever consumed. Future detectors might one day tune into these signals, reconstructing the history of long-dead stars from their final whispers. It's a staggering thought. The universe's most destructive phenomena might also be its most meticulous archivists, with cosmic strings serving as the silent librarians. Of course, not all physicists are convinced. Alternatives like holographic principal solutions or firewalls still vie for dominance in this debate. Yet the cosmic string hypothesis offers something unique, a tangible mechanism rooted in spacetime's architecture, not just abstract math. Whether it's the ultimate answer or another step toward one, this idea forces us to reconsider black holes not as cosmic dead ends, but as puzzles with threads, literally, leading us toward a deeper understanding of reality's most elusive rules. And that's the beauty of this paradox. It's not just about where information goes. It's about whether the universe respects its own laws, and if cosmic strings are the silent enforcers making sure it does. Gravity tugs at your feet with the gentlest of hands, while the other fundamental forces, electromagnetism, the strong and weak nuclear forces, wield power billions of times stronger. This baffling mismatch, known as the hierarchy problem, has long haunted physicists. Why is gravity the runt of the cosmic litter? The answer might be coiled in the universe's most elusive threads, cosmic strings. These spacetime defects could be hiding a clever loophole in nature's rulebook. While other forces operate at the quantum scale, gravity stretches across the cosmos, and cosmic strings might be the reason for this dramatic split. Picture the universe right after the Big Bang, when all forces were unified. As cosmic strings formed, their immense energy could have warped the fabric of reality itself, creating pockets where gravity leaked into extra dimensions while other forces remained trapped in our familiar four. The result, gravity appears feeble only because much of its influence is diluted across hidden realms we can't perceive. But there's another twist. Cosmic strings don't just hide gravity's strength, they might actively suppress it. Their gravitational pull could create localized fields that cancel out gravity's effects on small scales, like a cosmic muffler dampening an engine's roar. This would explain why gravity dominates galaxies but becomes negligible in particle collisions where other forces reign supreme. The implications are revolutionary. If cosmic strings mediate the hierarchy problem, they'd connect two seemingly separate worlds, particle physics and cosmology. Experiments at particle colliders might uncover clues in rare energy fluctuations, while gravitational wave observatories could detect subtle anomalies in spacetime's vibrations, both hinting at strings' hidden role in gravity's quarantine. Yet the mystery deepens. Some theories propose that strings don't just explain gravity's weakness, they might also predict its ultimate fate. If these defects decay over time, their fading influence could gradually alter gravity's apparent strength, a slow-motion unraveling of the universe's foundational balance. Whether cosmic strings hold the key to this puzzle or merely deepen it, one thing is clear: the hierarchy problem isn't just a quirk of physics, it's a cosmic whodunit. And the prime suspect might be hiding in plain sight, woven into the fabric of spacetime itself. 25th theory, cosmic strings and the nature of consciousness. What if the universe isn't just a stage for matter and energy, but for thought itself? At the farthest edges of scientific speculation, cosmic strings intersect with one of existence's deepest mysteries, the nature of consciousness. If these space-time threads warp reality at fundamental levels, could they also shape the way minds perceive, or even emerge within the cosmos? The idea sounds like science fiction, but it emerges from a daring collision of physics and philosophy. At its core is a radical notion: consciousness might not be confined to brains, but could arise from the fabric of spacetime itself. Proponents of theories like panpsychism suggest that awareness isn't an accident of biology, it's woven into the universe's structure. If that's true, cosmic strings, with their ability to bend spacetime geometry, might act as cosmic conductors, orchestrating consciousness in ways we can barely fathom. Think of it like this: every thought you've ever had is the result of electrical impulses dancing across neurons. But what if those neurons are just the tip of the iceberg? Cosmic strings could create subtle gravitational fluctuations, warping spacetime in patterns that influence quantum processes within our brains, like ripples in a pond nudging a boat's course. In this view, consciousness wouldn't be generated by the brain, but filtered through it, with strings acting as amplifiers or distorters of a deeper cosmic awareness. Skeptics, of course, dismiss this as wild conjecture. Consciousness is notoriously difficult to define, let alone link to hypothetical spacetime defects. Yet, intriguingly, certain neurological phenomena like spontaneous bursts of insight or altered states could hypothetically align with gravitational anomalies caused by nearby cosmic strings. Even the brain's electromagnetic field, which some believe plays a role in consciousness, might interact with these spacetime threads in ways we've yet to measure. The implications stretch beyond human experience. If cosmic strings influence consciousness, they might also shape the rise of intelligence elsewhere in the universe, or even determine where and when life can become self-aware. Some researchers speculate that regions densely threaded with strings could be hotspots for complex awareness, while voids remain mental deserts. It's a haunting thought. The universe's structure might not just dictate where stars form, but where minds awaken. For now, this remains a fringe idea, an intersection of metaphysics and astrophysics with little empirical grounding. But it raises a profound question. If we're truly products of spacetime, then unraveling the mysteries of cosmic strings might not just reveal how the universe works, but how it thinks. Whether fact or fantasy, the theory forces us to confront an exhilarating possibility: that the cosmos isn't just alive with matter and energy, but with something far stranger, the silent hum of a mind woven into reality itself. 26th theory, cosmic strings and the simulation hypothesis. What if everything we experience, stars, galaxies, even our own thoughts, is nothing more than lines of code in a vast, unimaginably complex simulation? This is the simulation hypothesis, a provocative idea that has moved from philosophy to serious scientific debate. And if it's true, cosmic strings might be the most revealing glitches in the system, errors in the program, intentional data structures, or even the seams where the simulation stitches reality together. Think of a cosmic string like a bug in a video game, an anomaly where the physics engine breaks down. In a simulated universe, these ultra-thin, ultra-dense defects could be artifacts of the underlying code, places where the computational framework strains under its own complexity. Maybe they're leftover fragments from an earlier version of the simulation, or perhaps they're deliberate markers placed by the programmers to organize space-time like a digital grid. Either way, their existence would be a smoking gun, hinting that reality isn't what it seems. The parallels are eerie. Just as computer code can generate random glitches, textures stretching unnaturally, objects clipping through walls, cosmic strings exhibit behavior that defies conventional physics. Their infinite thinness yet unimaginable density, their ability to warp time and space without emitting light, even their potential to form time loops, all of it looks suspiciously like the kind of shortcuts a simulation might take to conserve processing power. But here's where it gets even wilder. If cosmic strings are part of the code, studying them could give us a backdoor into understanding the rules of the simulation itself. Their gravitational effects, vibration patterns, or even decay processes might reveal the resolution of the universe's render settings, how finely detailed the simulation is, or whether there's a limit to how much data it can handle before glitches appear. Some physicists speculate that if strings follow predictable mathematical patterns, it could hint at an underlying algorithmic structure, like finding the source code for gravity itself. Of course, not everyone buys into the simulation argument. Critics point out that there's no direct evidence, just intriguing philosophical puzzles. Yet even if the simulation hypothesis remains speculative, cosmic strings force us to ask deep questions about reality's nature. Are they just cosmic accidents, or could they be the stitches holding together a constructed universe? Whether you find the idea exhilarating or unsettling, one thing's certain. If our existence is a simulation, cosmic strings might be the closest thing we have to a developer's signature, a hidden message waiting to be decoded. And that leaves us with a tantalizing thought. If we ever prove cosmic strings are real, will we also be one step closer to discovering that the universe isn't just governed by laws, but by lines of code? After an extraordinary journey through 26 astonishing theories, we're left staring at the cosmos with fresh eyes and more questions than answers. From bending time to stitching together parallel realities, cosmic strings have taken us to the edge of scientific imagination and beyond. These aren't just abstract curiosities, they're potential keys to unlocking the universe's deepest puzzles. Dark matter's grip, time's arrow, even the unsettling silence beyond our planet. What makes cosmic strings so captivating isn't just their strangeness, but their versatility. They could be relics, architects, destroyers, or even cosmic messengers all at once. Whether they are hiding in gravitational wave signals, imprinted on the cosmic microwave background, or vibrating unseen in the voids between galaxies, their existence would force us to rewrite not just astrophysics textbooks, but our very understanding of reality. Yet for all their grandeur, the hunt for cosmic strings is a race against time and technology. Will next-generation telescopes spot their telltale distortions? Could a breakthrough in quantum gravity suddenly make their detection inevitable, or will they remain ghosts in the equations hiding just beyond our reach? This isn't just science, it's a detective story spanning the entirety of existence. And like any great mystery, the answers might be stranger than anything we've dared to theorize. So what's your take? Are cosmic strings the universe's hidden scaffolding, or a beautiful dead end in our quest for knowledge? Drop your thoughts below. Let's keep the conversation as boundless as the cosmos itself. And if you've enjoyed this cosmic deep dive, hit subscribe so you don't miss our next adventure into the unknown. Until then, keep looking up and